One thing we need to do is talk about the concept of finding zeros a little bit more closely. Finding the zeros, finding the x-intercepts are all about solving the equation f of x equals 0. So if I'm trying to find the zeros of this polynomial here, I have to set this polynomial equal to 0 and solve it. Well, that's a polynomial equation, and the primary way you solve a polynomial equation is factoring. But sometimes looking at the polynomial and being able to factor it are not very easy things to do. You've learned a bunch of methods of factoring from algebra. Factoring out a greatest common factor, factoring some special products like the difference of two squares, factoring quadratics, but a lot of polynomials, don't use those methods of factoring. And what I call those methods that you learn in algebra are factoring by hand. So if you want to factor a polynomial, lots of times you need to try and think about it differently. And one way we can talk about factoring polynomials is through division. So if I look at this polynomial here, I can use division to help me factor this. Now, we're going to need to fill in some of the gaps that we have here. So it's going to take us a while to get to the point where we can factor this through division. So let's just look at a couple things. If I told you that one of your factors was x minus 2, which means one of your x-intercepts is x equals 2, or x equals 2 is a 0. They all are the same thing, remember. If I told you that, I could then ask you, well, if x minus 2 is a factor, what's the other factor? So the idea is, okay, that means my original function can be written as x minus 2 times something else. How can I find that other factor? Well, one way of finding that other factor is through division. If I take f of x and I divide it by x minus 2, that will get me that other factor. Because if you think about it, if you take this equation here, if I divide both sides of the equation by 2, by x minus 2, these x minus 2's will cancel, and what do I have? I have f of x over x minus 2 equals q of x. In that case, I'm finding q of x by doing this division. So what you need to know is, how do I divide polynomials? Well, you should be somewhat familiar with dividing one polynomial by another polynomial. There's two ways to do it. One is with long division, which is something that you should be somewhat familiar with, which we'll go over, and another one is synthetic division, which may be a new concept, may or may not be a new concept. So we'll look at both. Now the one thing is, long division, no matter what polynomials you're dividing, will always work. You'll always be able to do the division as long as the degree in the numerator is greater than or equal to the degree in the denominator. So if I'm going to do this division, I'm going to divide x minus 2 into 6x cubed minus 19x squared plus 16x minus 4. And the answer I get, the quotient I should get, will be this other factor. Again, because of this idea that f of x over x minus 2 should get me that q of x. Okay, just move this to the other side by dividing. So how do you do this long division? Well, the best way to do it is to say, how many times does x minus 2 go into this thing, this big long polynomial? But that's not a very easy question to go through, so what you should do is say, how many times does x go into 6x cubed? So if I'm doing that, really what I'm saying is, take 6x cubed and divide it by x. What do you get? You get 6x squared. So this goes into this 6x squared times. So then what I do is I take this, I multiply it by this, I get 6x cubed minus 12x squared, and I subtract. Now if I subtract, what I have to do is distribute this negative here and distribute this negative here, which makes this a plus. Okay, so I get the 6x cubed minus 6x cubed, they cancel. And then I have negative 19x squared plus 12x squared gives me negative 7x squared. Bring down the 16x. Then essentially repeat the process again. take the first term inside divided by the first term outside. So it's negative 7x squared divided by x. I get negative 7x. So negative 7x is the next term of my quotient. And what I'm doing here is I'm building the quotient. Okay. So negative 7x times x gives me negative 7x squared. Negative 7x times the negative 2 gives me positive 14x. This thing has to be subtracted. So when I subtract, I have to distribute this negative in here, and that makes this a minus. So then what I have to do is combine, so I get this becomes a plus, remember. I should make this a red. This becomes a plus. So then these cancel, and I end up with 16x minus 14x is 2x. Bring down the minus 4. And you just keep doing this, okay? You do this when the first term inside has a smaller degree than the first term outside. It's not smaller yet, so we keep going. One more time. 2x divided by x gives me 2. Place that here. Multiply, I get 2x minus 4. I subtract, I get 0. Now I got a remainder of 0. That's not by coincidence. You're not always going to get a remainder of 0, but for this factoring thing to work, that's going to be a key part to it, which we're going to have to talk about a little bit more. But that being a 0 is important. So you go through all this and say, alright, well, what were we trying to do? We were saying x minus 2 was one of my factors. X minus 2 was one of my factors. We were trying to find that other factor, okay? Well, that other factor is the quotient. So that tells me that f of x over x minus 2 is equal to 6x squared minus 7x plus 2. Or that f of x is equal to x minus 2 times 6x squared minus 7x plus 2. Okay? So given one factor, we came up with the other factor for the original polynomial through division. And one of the keys is that the remainder ended up being 0. When you're doing the long division, the keys that you gotta remember, the biggest one is this negative, distributing this negative through and then changing the sign here from a plus to a minus or a minus to a plus. That's usually where most students are going to make their mistake. So I distribute this in, it becomes a plus, and that's where I get a 0. That's usually where most students are going to make the mistake. And you mess up that, then this number right here is wrong. And if that number here is wrong, then this number here is going to be wrong, and so on. So you really got to concentrate on distributing that negative through so that you get your computation to be correct. Another thing you got to remember is when you're doing your long division, all your work's happening right here. So this thing has to be organized. I need to put x cubes over x cubes, x squared is going to be lined up, x to the first have to be lined up, and my constants have to be lined up. So what happens is my dividend, which is the thing inside the radical, inside the division bracket, has to be written in descending powers. And all those powers have to be taken care of, meaning if I was missing one, I would have to make sure there's a place for x squareds to go, even though I don't have an x squared in my original dividend. So this brings us to something called the division algorithm. The division algorithm is just basically telling you how you should write your answer when it comes to division, and then how that can then get us some methods of really factoring. So if I take one function divided by another function, and these can be numbers, these can be polynomials, it doesn't matter. If I divide one thing by another thing, I'm going to get an answer, which is a quotient, plus a remainder over divisor. You know, when you were in elementary school and you did division, you would write yourself as your quotient, and then you'd write r colon and write your remainder, right, which would be a number or whatever. That's not really acceptable to write your answer that way. The proper way to write your answer in sort of this equation format is to write your answer as your quotient plus your remainder over your divisor. The divisor is the original divisor. Now the remainder, if it's 0, would be 0 over divisor and you don't write it. But if your remainder is anything other than your divisor, anything other than 0, you put it over your divisor. Now, what the division algorithm does is it takes that equation, which is the proper way to write your answer, okay? And again, if I just do this real quick, this thing in here is my dividend, this is my divisor, this is my quotient, and in the end, after all this, the final line right here is your remainder. Okay, so when I look at this, I have divisor, this is that d of x, this is that f of x that you're seeing above here, this is the q of x, and this is the r of x. Okay, so when I place it all together, this is the way I write my answer. What the division algorithm does is it writes that whole thing in a slightly different way. It takes that equation that we just came up with from division, and if you multiply this whole thing through by d of x, okay, multiply d of x in here, here, and here. What happens is the d of x cancels this d of x when I multiply it times the first one. The d of x has to be multiplied by the q of x, and when I multiply the d of x into the third one, it cancels as well. So what I end up with is f of x equals d of x times q of x plus r of x, which is really my dividend equals my divisor times my quotient plus my remainder. And the key here is, in the last example, our remainder was 0. If your remainder is 0, this last piece is plus 0. We never really write plus 0 on anything because that's pointless. So what you really have is dividend equals divisor times quotient. Well, you have your dividend written as a product of two values. If you ever write something as a product of two values, it's factored. So this is essentially how division helps us factor. But the key is the remainder would have to be 0. If your remainder is not 0, then you don't have factors. So when we're looking at the division algorithm, that's really kind of the method of the division algorithm that will help us factor. Whenever you divide, you can get the remainder to be anything. What we're looking for is to divide by something specifically so that the remainder becomes 0. In this last problem, okay, I gave you this value x minus 2. And I said this is a factor, which basically said when you divide by this, the remainder will be 0. And I just needed you to find the other factor. What's going to happen in most cases is you're going to have to come up with the first factor that gives you a remainder of 0 and then also find the other factor. So we have a ways to go before we get there. So let's get some more practice with long division. Remember, key things you need to do before you do your division algorithm or you apply long division is make sure your dividend and divisor are both written in descending powers of the variable. Highest power first, then go down from there. Also, if you're missing a power for the variable, make sure that you have a place filler for one of those missing powers. So put a 0 as the coefficient for the missing power, and I'll show you an example of that. So if we want to divide x squared minus 3x plus 5 by x plus 1. So I have x squared minus 3x plus 5. And I want to divide that by x plus 1. So this is my dividend, this is my divisor. I'm not missing any powers for my divisor or my dividend. I start with a square, then I go to a first, and then I have a constant, and my divisor is the same way. So now I got to start this division. So what I'm going to do is take the first term inside divided by the first term outside. So I have x squared divided by x gives me x. So I put an x up here. I'm going to multiply this times this, which gives me x squared plus x, and then I'm going to subtract. Now the whole thing is being subtracted, so this negative has to distribute in here, and this negative has to distribute in here, which makes this a minus. Okay? That's most likely where you're going to make your mistake if you mess up, because lots of times when people distribute this in, they don't distribute it correctly, and then they don't subtract these numbers correctly. So I have the x squareds will always cancel. I have minus 3x minus x gives me minus 4x. Okay? Bring down the 5. First term inside by first term outside. I get minus 4. And that process just repeats itself until we're done. So we have a minus 4, multiply, I have minus 4x, minus 4. I subtract. I distribute. This becomes a plus. This becomes a plus. So then I end up with a 9 as my remainder. So in this case I got a remainder of 9, which is fine. You're going to get remainders sometimes. All that tells you is that we're not talking about factors here. When I take x squared minus 3x plus 5 and I divide it by x plus 1, I'm going to get a quotient, which is x minus 4, plus my remainder over my original divisor. And this is the way my final answer should be written. Okay, let's do another one. I want to divide x cubed minus 1 by x minus 1. So, x cubed minus 1 goes inside. Now the problem is I have an x cubed, but I don't have a square, I don't have a first power. So what I'm going to do is put a placeholder in there. 0x squared, 0x minus 1. Okay? So I don't have these two terms here in the middle, but I have a place for x squareds to go should I get any. I have a place for x to the first to go should I get any. 0x squared is like 0, 0x is like 0, so basically I'm adding 0 on, which doesn't change the original polynomial. X minus 1 goes outside. And then the process starts the same way. Take the first term inside, divide it by the first term outside. So x cubed divided by x gives me x squared. Place it in my quotient. Multiply these together. X cubed minus x squared. And this is why I needed that x squared place filler. Because when I go to distribute this negative, this is going to be a minus, this is going to be a plus, and I have an x squared that needs to be added to another x squared, and now I have it. 0x squared plus 1x squared gives me 1x squared. Bring down some more. Start the process again. First term inside divided by first term outside. X squared divided by x gives me x. And I place that here. X times x is x squared. X times minus 1 is minus x. Subtract. Distribute the negative in. Minus plus. Again, 0x plus 1x gives me a 1x. Bring down the minus 1. And I keep going and going. Divide again. X divided by x gives me 1. Put a plus 1 up here. Multiply. I have x minus 1. I subtract. I get 0. So what does that tell me? It tells me that x cubed minus 1 divided by x minus 1 equals x squared plus x plus 1 plus 0 over x minus 1. Quotient plus remainder over divisor. But since this is 0 over x minus 1, we don't really have to write that. So essentially, x cubed minus 1 times x minus 1 equals x squared, or x cubed minus 1 divided by x minus 1 equals x squared plus x plus 1. And what this really tells me is if I multiply this to the other side of this equation, x cubed minus 1 equals x squared plus x plus 1 times x minus 1. And what I really have are factors for this particular polynomial. Again, this is kind of where we're going with this whole thing eventually, but you got to be able to divide before we can get there. But that's kind of where this thing is going. So in this one we do have factors, whereas the last one we didn't have factors. Now there's an alternative method to long division, which is really just a shortcut for long division called synthetic division. The one problem with synthetic division is that you can't do it all the time. If you're ever dividing two polynomials together, you can use long division to do that division. But what you can't do is use synthetic all the time. Synthetic division only works when your divisor is of this form, x minus k. Really, it's what it is x plus or minus a number. Okay, that's really what you're looking for your divisor to be. if your divisor is of that form, that's when synthetic division will work. So we're taking some polynomial, okay, f of x, and we're dividing it by something in the form x plus or minus a number. That's it. If you're not dividing by x plus or minus a number, you cannot do synthetic division, okay? So when I'm trying to do synthetic division, there are a certain amount of steps I need to go through to do synthetic division. And what happens is this is related to long division. So what I have to do is do a lot of things that I do with long division the same, at least to set it all up. So first thing is my dividend, which is the thing inside the division bracket. That has to have all the powers in descending order. If I'm missing a particular power, I have to have a 0 as its coefficient. And what I'm going to do is list all those coefficients inside the division bracket. Then what I'm going to do is I'm going to place the value of k outside the division bracket. Now there's something you're going to have to watch out for. You're going to have to watch out for your signs, because we're going to place k outside the division bracket. If you look, k is what's being subtracted. Just k is going to go outside, not this minus k, but k itself. So you got to think about what's being subtracted here in this x minus k. Then there's going to be a pattern to it. What's going to happen is we're going to create this pattern of vertical terms and diagonal terms. Diagonal terms are created by multiplication, vertical terms are created by addition, and then what happens is our result are our quotients, coefficients. So this is the way it's going to look. If I do the same problem I just did, if I take x cubed minus 1 and divide it by x minus 1, right, that's what I want to do. We already know the answer is x squared plus x plus 1, okay? And we did that through long division a second ago. Now I'm going to do it through synthetic division. So what I'm going to do is I'm going to do an upside down division bracket. I'm going to place the coefficients for my dividend inside. The first coefficient is a 1. That's in front of the x cubed. There is no x squared, so the coefficient there is a 0. The coefficient for the x to the first is a 0, and the constant is a negative 1. So those are the coefficients. If I take a step back to the previous example, look at what we did for our coefficients. 1, 0, 0, negative 1. That's what's inside the division bracket. Okay, let's go back again. Outside, I'm going to place k. K is what's being subtracted. In this case, that value right there is k, so I'm going to put a 1 here. The easiest way to remember what to put out here is the opposite of what you see here goes here. So if this is an x minus 1, I put a plus 1 here. If this was x plus 1, I'll put a minus 1 here. Now there's a reason for it. When we do long division, we subtract line from line from line. But that subtraction can cause some issues in that you have to distribute the negative. What I want to do is avoid having to distribute the negative. So what I'm going to do is distribute the negative here, so I don't have to distribute the negative everywhere else. And that's going to be basically changing that sign. If I take a step back to the previous problem, it's like this. I multiply this times this. If I look and I multiply this x squared times this negative 1, and I got a negative x squared. But then I took this negative here and distributed it and became a positive. Well, if I just would have changed this one out here to a positive first, then when I multiplied x squared times 1, I would have already had a positive x squared, and I wouldn't have to worry about distributing this negative in. So that's kind of the idea here, is we're changing from subtracting line after line after line to changing this sign here, and then what we can do is add line after line after line, because this sign here will already be changed. Okay, in this case it would have been a plus because of the distributing of the negative inside. Alright, so let's go back to where we were. So I have this 1 here, so I put all my coefficients inside, put the opposite sign of this number outside. What I'm going to do is bring this first number down. Okay, now I'm going to take this number here, and I'm going to multiply it by that number there, and I'm going to place it diagonally. Remember, diagonal pattern is to multiply. So I'm going to get a 1. Then this vertical pattern, I'm going to add. Normally in division you subtract, but because we use the opposite sign, we can now add. I get a 1. I'm going to repeat this again. Multiply this times this, place it here, I get a 1. Add, I get a 1. Do it again, I get a 1. Right? add straight down. Again, I get a 0. These are just a set of numbers, okay? But these numbers are my answer. The last number in the row will be your remainder. This right here is your quotient. Now, the way you can write your quotient is that the first one's going to be your constant, and just start increasing the power for your variable from there. So this will be 1, this will be a 1x, this will be a 1x squared. And that's going to be what my quotient looks like. So when I take this, if you look, the quotient I got here is the same thing I got before. 1x squared plus 1x plus 1 is my quotient, and my remainder was 0. It seems a little crazy, but if you follow it, okay, oops, sorry, I skipped too far. If you follow it, the computation that we're doing here, now I know this thing looks like a mess, but the computation we're doing here, and here, and here, is the same computation that we're doing here, here, and here, okay? So obviously we're going to have to do more examples of this, but this is a faster way to get this division done. So let's do this one. Use synthetic division, divide this polynomial by this polynomial. Look at what you're dividing by. I'm dividing by x plus 2, which is in the form of x minus k, because I could write this as x minus negative 2. So really, x plus a number or x minus a number is what you're looking to divide by. That's the only time you're going to want to use synthetic division. So what I'm going to do is I'm going to take my dividend, and I'm going to place it inside, but just the coefficients. I have a 4. I don't have a cube, so I'm going to put a 0, a minus 2 for my x squared, a minus 1 for my x, and a plus 1 for my constant. You want to make sure that anything that's missing has a 0 in for it, even if your constant is the one that's missing, okay? If there's no constant on the end, you would put a 0 on the end. Outside, I'm going to put a minus 2, okay? Because if I think about the opposite of this would be a minus. Or I can say what's being subtracted. The minus 2 is being subtracted. That's my k. That's what I'm going to place outside. However you want to think about it, I think the easiest way for most people is to say, let's just do the opposite of what's here. So I'm going to bring the first term down, which is a 4. Then I'm going to multiply these together. That's going to give me a negative 8. Then I'm going to add vertically. So that gives me a minus 8, and continue this process. I want to get a positive 16, because again, I'm always multiplying this times this. I add straight down. I'm going to get a 14. Multiply again. I get a negative 28. Add, I get a negative 29. Multiply one more time. I'm going to get a positive 58. Add, I get 59. Okay. So now I got to make sense of this. The last number on the end is always going to be your remainder, and the rest of it's going to be your quotient. So make sense of your quotient. This is your constant, and work your way back the other way. So this would be an x, this would be an x squared, and this would be an x cubed. So I have 4x cubed minus 8x squared plus 14x minus 29 plus 59 over the original divisor, which is x plus 2. Now you always put it in the over the original divisor. Don't do x minus 2 here, because you changed it to a minus 2 here. That minus 2 out here was just changed so you can do the computation. You should still always write your answer as quotient plus remainder over divisor, and what you were dividing by was x plus 2. So this is the answer for the division. Now that was a heck of a lot faster than doing long division, but we can't always use synthetic division. We can only use it sometimes, and that's depending on what we're dividing by. Let's do one more. Take 3x to the third minus 4x plus 1 and divide it by x plus 1. So I'm going to take a 3, 0, minus 4, and a 1. This is my cube. I don't have a square, my first power, and my constant. Out here I'm going to put a minus 1. I'm going to bring the first term down, and I'm going to multiply and get negative 3. Add, I want to get negative 3. Multiply, I get positive 3. Add, I get negative 1. Multiply again, I get positive 1. Add, I get 2. So remainder, quotient. In this case, my quotient is going to be 3x squared minus 3x minus 1, and my remainder is going to be 2, so I put 2 over x plus 1. So that's how I do synthetic division. Now that we have the skills to do synthetic division and even long division, there are two theorems we need to discuss, the remainder theorem and the factor theorem, that basically will get us to the point where we can use division to help us factor. I've already given you the basics of how we're going to use these two theorems, but now we got to concretely write down kind of how division helps us factor. So let's look at the remainder theorem. If we look at the remainder theorem, the remainder theorem is stated as such. If a polynomial f of x is divided by x minus k, remember, if that's the case, we can use synthetic division, then the remainder we get will be equal to f of k, which basically tells us that the remainder theorem is a method for evaluating functions but using division to do so. If I am trying to find, if I have a function, f of x, and I'm trying to find f of 3, one thing I can do is I can take 3 and plug it into the function and then evaluate it. Something you should have done when you learned functions initially. But what this thing is saying is if I want to find f of 3, I don't have to just take 3 and plug it into the function and get my answer. What I can do is take my original function, divide it by x minus 3, and the remainder I get, because remember I'm going to get a quotient plus remainder over my divisor, which is x minus 3. The remainder I get will be f of 3, okay? Which is just an alternative way of evaluating functions, but through division. Now, if we're dividing by x minus 3, or if we're dividing by x minus k, we can use synthetic division. And when you do synthetic division, the last number you get in the row, whatever it is, that's going to be your remainder. So that's going to be f of whatever the opposite of this is. Okay, or sorry, f of whatever this number is here. So let's see it in an example. So use the remainder theorem to find f of negative 2 for this function. Now the key is it says use the remainder theorem. One way to find f of negative 2 would be to do 4 times negative 2 cubed minus 2 times negative 2 squared plus negative 2 plus 3. But that's not using the remainder theorem. That's just taking negative 2 and plug it into the function. If I want to use the remainder theorem to find f of negative 2, what I should do is take f of x and divide it by x minus negative 2, or in this case x plus 2. So if I'm dividing by x minus negative 2 or x plus 2, what I'm going to do is do synthetic division. I'm going to take 4 minus 2, 1, and 3, because those are my coefficients for f of x. Place that inside, put a minus 2 outside. Remember, x minus this number is what you're dividing by. That's my k. That's f of k. So that's the number I place here, because if I'm dividing by x minus that, really what I'm dividing by is x plus 2, and I should put the opposite of x plus 2, which is minus 2, in here. Alright, so that tends to be tricky for some people, but the easiest thing is whatever you're finding f of, that's the number that goes there. So bring down the 4, multiply, I get a negative 8. Add straight down, I get a negative 10. Multiply again, I get a 20. Add, I get a 21. Multiply again, I get a negative 42. Add again, I get a negative 39. The last number in the row is your remainder. So what does that tell me? F of negative 2 equals negative 39. And that is how you evaluate a function using the remainder theorem. I think that is much easier than doing this. Okay? This computation, while it's not hard to do this computation up here, it does take some time. And here I'm just doing multiplication, addition, multiplication, addition, multiplication, addition, and coming up with this answer. It's much faster in the long run. Especially, think about it, if your polynomial is really, really large, and that means you have very high powers, raising numbers to higher and higher powers gets really big and fairly complicated. This stays fairly simple the whole time. But that's how the remainder theorem works. If a polynomial f of x is divided by x minus k, then the remainder will be f of k. So then the other theorem we need to discuss is the factor theorem. The factor theorem says a polynomial f of x has a factor x minus k if and only if f of k equals 0. Well, remember, f of k is going to give me the remainder. So what this is really saying in conjunction with the remainder theorem is that the remainder is 0. So if you combine the remainder theorem and the factor theorem, what you're basically saying is if you take a function f of x, divide by x minus k, and the remainder is 0, then x minus k is a factor. Okay? So if I wanted to say show that x minus 2 is a factor of x to the 4th minus 1, there's two ways to do it. One is if I find f of 1 and I get 0. That's saying take k, plug k into the function. If I get 0, which is basically what the factor theorem is saying, then, so I should say if f of 1 equals 0, then x minus 1 is a factor of x to the 4th minus 1. Okay? Well, you can clearly see that's going to be the case, right? If I do f of 1, I do 1 to the 4th minus 1, which gives me 0. So f of 1 is a factor. But I could also do it this way. Say, let's take f of x and divide it by x minus 1. And if the remainder equals 0, then x minus 1 is a factor. Okay? This second way is more beneficial in the long run because not only does it tell you that x minus 1 is a factor, this second method will also tell you what the other factor is, the quotient. Whereas in the first method, all that's going to tell you is whether or not x minus 1 is a factor, but you have no idea what the other factor is going to be. So I can do synthetic division. I have 1, 0, 0, 0, minus 1. Why do I need all these zeros? Because I don't have an x cubed, I don't have an x squared, and I don't have an x to the first power in my f of x. Outside, I'm going to put a positive 1 because I do the opposite sign. Bring the 1 down, multiply, add, multiply, add, multiply, add, multiply, add. Remainder 0. So since the remainder is 0, since the remainder equals 0, x minus 1 is a factor. But also, the other factor is my quotient. So I could say x to the 4th minus 1 equals x minus 1 times x cubed plus x squared plus x plus 1. That's what this is here. This is a constant of 1, x to the first power is 1, x to the second power is 1, x to the third power is 1. So the second method tells you whether or not x minus 1 is a factor, just like the first method does, but it also gets you the other factor. Okay, so either way, depends on the question. You know, if a question just says show that something is a factor, you simply could just take this number that's being subtracted here, plug that number into the function and see if you get 0. If you do, it's a factor. Fine, but if the question said find all the factors of this, okay, then the second method is probably better because it gets you more factors. Let's go to another one. Show that x minus 2 and x plus 3 are factors of this. So again, two ways to do it. I can take 2, plug 2 into the function and see if I get 0. I could take negative 3, because remember this is minus negative 3. I could take the negative 3, plug that into the function and see if I get 0. If either of them give me 0, it's going to tell me whether or not either of these are factors. But what I can also do is divide by each one of these to find whether or not it's a factor, but that can also tell me whether or not the next one's a factor, because I might get that one out of the division as well in my quotient. So let's do that. So I'm going to take 2, 7, negative 4, negative 27, negative 18, and I'm going to put a plus 2 out here, bring this 2 down, multiply, I get a 4, add, I get an 11, multiply, I get a 22, add, I get an 18, multiply, I get a 36, add together, I get a 9, multiply, I get an 18, add, I get a 0. So because I got the remainder to be 0, x minus 2 is a factor, which means f of x can be written as x minus 2 times something else. What's the something else? The quotient. 2x cubed plus 11x squared plus 18x plus 9. Now we want to check to see if x plus 3 is also a factor. I can do this whole thing over again, and I can put a minus 3 right here and then go through the process. But I don't need to do it that way. I can do this a little bit better in that if x plus 3 is going to be a factor of this, okay, I've already determined that x minus 2 is a factor. So this is the leftover piece. If x plus 3 is going to be a factor, x plus 3 has to be a factor of the leftover piece. Or x minus 2, but you can clearly see that x plus 3 is not a factor of x minus 2, so then it's got to be a factor of what's left. So really what I have to do is take my synthetic division and put the minus 3 out here, but instead of putting the original function, I can simply put this quotient inside, which is smaller, less computation, and I can check to see if x plus 3 is going to be a factor. So I bring the 2 down, I get a negative 6, I'm going to get 5, negative 15, I'm going to get 3, negative 3, 0. So I get a remainder of 0, so that means x minus 3 is a factor not only of this polynomial here, but of the original polynomial here, f of x. And it's kind of because if x minus 3 is if x plus 3 is a factor of this, and this one is a factor of this one, then x plus 3 is a factor of the original. Now look at what we have now. If we sort of look at this and break this apart, let's get rid of some of this stuff here. I need some space, so I'm going to erase some of this just to get a little bit of space in here. X minus 2 was a factor, right? And then what we really did is factored this leftover piece as x plus 3 times 2x squared plus 5x plus 3. So x minus 2 is a factor, x plus 3 is a factor, and then also 2x squared plus 5x plus 3 is yet another factor. If I can keep factoring this polynomial, 2x squared plus 5x plus 3, then what I'm doing is basically whittling down the original polynomial into all its smallest factors. And this is how we use division to help us completely factor a polynomial, which would then help us find the zeros of that particular polynomial. So just to review, we want to use the factor theorem and the remainder theorem with synthetic division to help us factor. So 1, the remainder obtained in synthetic division by dividing f of x by x minus k gets you the following info. The remainder will be essentially f of k. That's what the remainder theorem tells you. And if the remainder equals 0, then x minus k is a factor of f of x. And also, if the remainder is 0, then k comma 0 is the x-intercept for f of x. And also, k is considered to be a 0 of f of x. Okay? Remember, the degree of the polynomial will have at most that many zeros. So if we have an nth degree polynomial, it has n real zeros. At most, though, remember, it could have less than that. Some zeros may be complex. These do not relate to x-intercepts, so we ignore them. Okay, we talked about complex imaginary numbers. We're not going to have them. If you see them pop up in the textbook or anywhere else right now, just ignore them. They do have significance, but not to what we're doing immediately right now. So if I told you to find the factors of x cubed plus 2x squared minus x minus 2. What you'd have to do is figure out what could I divide by that would give me a remainder of 0. Now, we don't have a starting point. All the examples I gave you previously have given you something that is a factor and you work off of that. Most of the time you're not going to have that. So what we need to do is come up with that factor. Now, right now, there's not a great way to do it. I'll give you a way to do it in a second, but right now you just say, okay, I just got to try something. So what I'm going to do is say, what can I use synthetic division for to get a remainder of zeros? Well, 1, 2, -1, -2, I'm going to put inside. So what I can do is say, alright, well, let me just try something out here and see if it gives me a remainder of 0. It's not the greatest way to do things, but if I just put a 1 there, what's going to happen? 1 times 1 is 1, add I get 3, multiply I get 3, add I get 2, multiply I get 2, and aha, got a remainder of 0, which tells me that one factor is x minus 1. And once you get one that works, it all starts falling into place from there, because then the other factor is x squared plus 3x plus 2. That comes from the quotient. And then you keep factoring from that. Remember, find the factors. We want to find all the factors. Well, once you get down to the point where it's something that you can factor by hand, which you might have looked at the original one and tried to factor that by hand, maybe tried factor by grouping, but in this case we use division. Once you get to the point where something can be factored by hand, then you go ahead and do that. So this would be x minus 1 times x plus 1, x plus 2. This will give you x squared, then you get 2x, 1x is 3x, and then you get a 2. So this is going to be my factors. So then if I found all the factors of the polynomial, I am done. And I started it through division and then sort of finished it off by using the things I learned in algebra. So, you know, it's not the greatest way to do it is to just say, let's pick a random number out here and see if it works. But right now, that's kind of all you have. So one thing we need to talk about a little bit more detail before we move on is repeated zeros. I mentioned repeated zeros earlier, but now we need to talk a little bit more detail about repeated zeros and what they really mean. So we saw that sometimes a zero can be repeated, and that it can happen more than once. And really what that's going to happen is largely is when a factor occurs more than once. So you're looking at a factor like x minus a or something like that. And if a factor is occurring more than once, you could raise it to a power 2, 3, 4, 5. Well, the idea is that the 0 from that factor would be x equals a, and the number of times that that factor occurs, which is the power on the factor, we consider to be the multiplicity. Now, that multiplicity being even or odd affects how that 0 behaves on the x-axis. If your multiplicity is odd, your graph will cross the x-axis at that particular 0. However, if your multiplicity is even, the graph will only touch the x-axis at that 0 and then bounce off. So another way to think about it is that your polynomial will change signs when you have an odd multiplicity, and your polynomial will stay the same sign when you have an even multiplicity. So an example would be something like this. Say I have some function g of x, and I factor it, and I get down to x plus 1 to the third times x plus 2 times x minus 1 to the second. I have 3 zeros for this particular polynomial. In that case, I get x equals negative 1 is 1 0, so these are my zeros. I have x equals negative 1, x equals negative 2, and x equals positive 1. These are my zeros. They came from each one of these factors. Now, they also have multiplicities. In that case, the multiplicity for this is going to be 3. The multiplicity for x plus 1 is going to be 1, and the multiplicity for x minus 1 is going to be 2. These are my multiplicities: odd, odd, and even. Okay? So what does that mean? If I look at these are zeros, but really what they are x-intercepts. So if I think about this as the x-axis, I have an x-intercept at negative 2, at negative 1, and at positive 1. So as my graph is approaching this particular x-intercept, okay, let's say it's approaching it this way, or this way, okay? What's going to happen is my graph, as I approach this x-intercept, since this one had an odd multiplicity, this is the first one, right? So it's got an odd multiplicity. If I'm coming at it this way, I'm going to cut through the x-axis. Or if I'm coming at it this way, I'm going to cut through the x-axis. Whereas, say, this one over here, which was this 0, that had even multiplicity. If I'm coming at this x-intercept this way, here's my x-intercept, I'm going to just touch the x-axis and bounce right back off because it had an even multiplicity. Or if I was coming at it this way, I'm going to come up to the x-intercept and I'm going to bounce off because the idea had even multiplicity. I'm not going to cut completely through. In that case, my polynomial is not going to change signs, meaning it's not going to go from negative to positive. So let's do this example. Find all the real zeros along with their multiplicities for this particular function. So we need to start factoring it. Again, where do we start? Well, right now we don't have a good way to do it other than let's just start trying things. I'll put 1, negative 2, negative 3, 8, negative 4 inside. And I'm just going to start trying different numbers out here. So I'll try 1. If that doesn't work, I'll try minus 1 and keep going. So I go 1 times 1 is 1. I get a minus 1. Multiply again, I get a minus 1. I get a minus 4. I get a negative 4. I'm going to get a 4. I'm going to get a 4, and I get a 0, and bingo, I got one that works. So that tells me that one factor is x minus 1, and the other factor is this quotient. So now what I'm going to do is I'm going to divide this one again. The leftover piece I'm going to keep dividing. So what am I going to do? I'm going to try 1 again. I'm going to keep trying 1 until it stops working. So I go 1 times 1 is 1. This is going to give me a 0. This is going to give me a 0. I'm going to have a minus 4. I'm going to have a minus 4. And I got 0 again. So that's going to give me another one. So that means x plus 1, x minus 1 again is a factor. Now I'm going to try it again. Now actually what I can do is I can stop doing division. Look at what this is. Constant here. X to the first, x to the second. So really what I have is x squared minus 4. Do I have to divide to keep factoring that? Hopefully not. What I can do is do x minus 2, x plus 2. So what I have is, these are my factors for that polynomial. This one occurs twice. I can write this as x minus 1 to the second times x minus 2, x plus 2. So what I'm looking at here are zeros of 1, 2, and minus 2. And they have corresponding multiplicities of 2, 1, and 1. Okay? Which means I got an even multiplicity, odd, odd multiplicity. So if this is my x-intercept, if on my x-axis, my x-intercept is 1, say this is the x-axis. If I'm coming at this x-intercept this way, I'm going to bounce off the x-axis and move up. Or vice versa. If I'm coming at the x-intercept this way, I'm going to bounce off and move back down because I had an even multiplicity. For these odd multiplicities, I'm going to come at an x-intercept and I'm going to cut right through the x-axis. Alright. So now we need to have a better way of doing that division to factor rather than just start trying things. And that's where this rational zero test is going to come into play. So when I'm doing the rational zero test, right, I'm looking for values that will possibly work when I'm dividing. Values that will possibly give me a remainder of 0. Now, the only way I can do that is really this rational zero test. So the rational zero test says this. If I'm looking at a polynomial, and that polynomial is of this form, right? This is our standard form for a polynomial. There are two things I need to do. I should look at the constant, that's the number on one end, and the leading coefficient, that's the number on the other end. You don't want the leading coefficient to be equal to 0. And it never should be equal to 0, because if it's 0, then it's not the leading coefficient. It's not really there. The next one is the leading coefficient. But anyway, you don't want either of these things to be 0. You don't want the constant or the leading coefficient to be 0. What you're going to do is, if you want to find the possible things that will work in division, the things that will possibly give you a remainder of 0, the rational zero test says I should look at factors of the constant and factors of the leading coefficient. And if I divide those two things, okay, whatever I get will be the possible rational zeros. Okay? Now, one thing is that this only lists the possible rational zeros. This doesn't tell you what will work when you do the division. It just tells you what will possibly work. And you have to look at all the factors of the constant and all the factors of the leading coefficient and divide them in, you know, as many different ways as possible so that the constant's on top and the leading coefficient's on the bottom. And all those values I get from that will get me my possible rational zeros. The biggest thing I see students mess up is they don't put the constant factors on top and then the leading coefficients on the bottom. Constants on top, leading coefficient goes on bottom for my fraction. So the best thing to see here is an example, and I think it makes sense right away once you start to see an example. So look at this example. Find the possible rational zeros. So if I look at that and say find the possible rational zeros, well, the leading coefficient a sub n is 1 and the constant a sub 0 is -6. So if I look at the possible rational zeros, I got to look at factors of this. So what are factors of -6? Well, that would be 1, 2, 3, and 6. But they could also be positive or negative, because I could have positive 1, -6, positive 6, -1, and so on. So these are my possible factors. If I look at factors of 1, well, really all I have is 1, but actually plus and minus 1, because I have positive 1 and positive 1 and -1 and -1 will get me 1. And pretty much for all this, you're going to have plus and minus for all of them. So then I take all of these divided by all of these. So if I'm going to list my possible rational zeros, okay, I have to say, okay, let's do 1 divided by 1, and I'm going to get 1. Plus or minus, because you can have the positive. Let me take 2 divided by 1. That's going to be 2 plus or minus. 3 divided by 1. And 6 divided by 1. So these are the possible rational zeros, which means when I do synthetic division, if I'm trying to find the factors of this, when I do my synthetic division and I put 1, 0, -7, -6 inside, the only things I need to try outside would be any one of these numbers. So there's 4 of these plus and minus, so 8 of them total. What I don't have to try, what this tells me is that 4, because it's not in this list, 4 will never work here to give me a remainder of 0. Or 5, or 7, or any number that's not on this list. These are the possible ones that will work. Now this question said just find the possible rational zeros. It didn't say what are the zeros. It said just find the possible ones. And this is all you have to do when you find the possible rational zeros. Look at the next question. This one doesn't say find the possible rational zeros, but this says find the rational zeros. So what we're going to do is first we're going to list the possible rational zeros. Then we're going to find which ones actually are zeros. So let's do this. The constant, that's a sub 0, that's 1. Factors, plus and minus 1. The leading coefficient, that's a 1. Factors, plus and minus 1. If I divide them, my possible rational zeros are going to be plus and minus 1. All of these divided by all of these. So all I got is plus and minus 1. Now those are the possible ones, but the question said find the rational zeros. So now I got to figure out which one of these work. But here's the thing. These are the only things that will possibly work. So if I go like this, I say, okay, 1, 0, 1, 1. Right? Because that's what this polynomial is up here. I'm missing the square, so that's why I put the 0. And I'm going to put a 1 here. So bring down the 1, multiply, I get 1, add, I get 1. Multiply again, I get 1, add, I get 2, multiply, I get 2, add, I get 3. I don't get 0. Therefore, x equals 1 is not a 0. Try -1. Put -1. What am I going to get? I'm going to get -1, -1, +1, 2, -2, -1. That's not equal to 0. Therefore, x equals -1 is not a 0. Okay? So if -1 is not a 0 and +1 is not a 0, and these are the only possible rational zeros I have, how can I find the rational zeros? Well, there aren't any in this particular case, because these were the only possible ones that would work. Neither of them do work, so in this case what I can say is that there are no rational zeros. Now that doesn't mean that there's no zeros, period. It just means that there's no rational zeros. Rationals are numbers that can be written as a fraction. So the only other possibility is that there's something called irrational zeros or imaginary zeros, which the irrational zeros are not going to be able to be found unless you use something like the quadratic formula. This is a cubic, so that's not going to work. And the imaginary ones we said we're ignoring. All right, let me give you one more example. So list the possible rational zeros for f of x equals, let's say 5x to the 4th plus 3x cubed minus 6x squared plus 127x minus 12. Now remember, this just says list the possible. We don't have to figure out which ones actually work, just list which ones will possibly work. So these are the two numbers that are important. So what I'm going to do is I'm going to say, okay, A sub 0 is negative 12. Factors 1, 2, 3, 4, 6, 12. Plus and minus 1, all of them. And it's always going to be plus and minus, regardless of whether or not the original number is positive or negative. Because two negatives can get you a positive, two positives get you a positive. When it's negative, you have a positive and negative. So any way you do it, you can get a positive and a negative. A sub n is this 5. We got these factors. 1 and 5, again, plus and minus, right? I could get negative 1, negative 5, positive 1, positive 5. So when I'm looking at all this, okay, I'm going to take any one of these divided by any one of these, and what I'm going to get, my possible rational zeros will be 1 divided by 1, 1 divided by 5. 2 divided by 1, 2 divided by 5. 3 divided by 1, 3 divided by 5, and so on. So I get 1 divided by 1 is 1. 1 divided by 5 is 1/5. Again, plus or minus on all this. 2 divided by 1 is 2. 2 divided by 5 is 2/5. 3 divided by 1 is 3. 3 divided by 5 is 3/5. 4 divided by 1 is 4. 4 divided by 5 is 4/5. 6 divided by 1 is 6. 6 divided by 5 is 6/5, etc. 12, 12/5, plus or minus. These are all the possible rational zeros. There's a lot of them in this case. So you look at this, there's really double what I have here because they're all plus and minus. Any one of these things could possibly work. So if I'm trying to actually find the factors of this or find the zeros of this polynomial, and I'm doing synthetic division, any one of these numbers is a possibility to try here. Now if I was doing this for real, I would say, alright, let's try these numbers first because they're easier. But if they start to fail, then I got to go back and actually put fractions here, which is a possibility. You might have to do that, but it's rare. It's a possibility though. So that wraps up pretty much the major things you need to know about zeros, finding zeros through division, finding zeros using the rational zero test, your remainder theorem, your factor theorem, and repeated zeros.